everyone, I'm Professor Harrison and welcome back to our module on regression. Today we're going to write a regression model in matrix form and use it to build a single formula that estimates all the coefficients at once. We're following Margot, a graduate student trying to reassemble a story her family buried. Today she's looking at how a single fund's return tracked the market over a handful of months. Decades ago, an anonymous correspondent of her grandfather's had already worked out this exact problem, all using the language of matrices. She pulls up another one of those mysterious letters. Back in the OLS videos, we found the slope and intercept for a single explanatory variable. The slope was the covariance of the two variables over the variance of the explanatory one, and the intercept fell out from there. That worked out cleanly because there was only one slope to find. But once you have several explanatory variables, writing a separate scalar formula for each coefficient gets really unwieldy fast. So we need a way to write the whole thing down at once, no matter how many variables there are, and that's what matrix notation is going to give us. So here's the setup. Stack every observation on top of each other. The outcome becomes a single column vector, and we're going to call that y. And here y has one row per observation. The coefficients then become a column vector too, which we're going to call beta, with the intercept on top followed by each of the slopes. Then the explanatory variables are going to go into a matrix which we're going to call X, the design matrix. The design matrix is the piece worth slowing down on. Its first column is all ones. Then each remaining column holds the explanatory variable with one row per observation. That first column is how we handle the intercept. It's the column that makes it so that when you do matrix multiplication, the intercept gets carried through the matrix machinery automatically, just like any of the other coefficients. We put it together and the entire model collapses into one line, y equals x times beta, plus the error vector. The nice thing about this notation is that it could hold 2 observations or 2,000. It could also hold one explanatory variable or 50. It's very versatile and can be used in any multiple regression setting. Now we want the best fitting coefficients. Using the same OLS criterion as before, we're minimizing the sum of square residuals. We carry that minimization through in matrix form, and you land on the formula that runs all of the regression. Beta hat equals x transpose x inverse times x transpose y. Let's read that slowly because every piece is something that we built out in the matrix module. X transpose is the design matrix with its rows and columns swapped. Multiply X transpose by X and you get a small square matrix. Then we invert the square matrix, which is exactly the matrix inverse we worked through in Module 4. Then finally we multiply by X transpose times Y. So we just use the transpose matrix multiplication in the inverse. That's the whole recipe that's used to run a regression. Now let's see it on Margot's fun. We have one explanatory variable, which is the market return, plus the intercept. So the design matrix X has 2 columns, the column of ones for the intercept and a column of the market returns for each month. With one explanatory variable, X transpose X comes out as a 2 by 2 matrix, which is the size we know how to invert by hand. We run the formula and get beta hat equals X transpose X inverse times X transpose Y, and it hands back 2 numbers. It gives us the intercept and the slope on the market. And here's the reassuring part. Those 2 numbers are going to be exactly the intercept and slope that you get if you use the covariance over variance formula that we used before. The matrix machinery didn't change the answer, it just repackaged it. The slope itself is the fund's sensitivity to the market, it's beta. And a slope near 1 says that the fund roughly moves up and down with the market. So what's the advantage of using the matrix form over using the covariance variance formula? The main benefit is that it doesn't care how many variables you have. Stack a second column into X, a third, a tenth, and beta hat equals X transpose X inverse times X transpose Y. We still have the same formula. Every coefficient all at once, no matter how wide the model gets. That's why matrix form is the standard notation. It's what your computer is actually doing under the hood when you run a regression, and it's the foundation for standard errors, the tests, and the diagnostics that come later in the module. There is one thing that the formula needs. X transpose X has to be invertible. If 2 of your explanatory variables carry basically the same information, then that inverse doesn't exist and the whole formula breaks down. That turns out to be a real problem of its own, and we're going to come back to it later on in this module. Margot sets down the letter next to a stack of her grandfather's old academic papers. The notation in the letter matches the notation in the papers almost exactly. It's not just the same math, but even the same way of writing it, down to the same shorthand and the same idiosyncratic ways of stacking the matrix design and talking about them. Whoever wrote those letters and whoever wrote the papers learned the method from the same source. Margot just doesn't yet know what that source could be, but now she has her first clue. So that's the matrix form of regression. We stack every observation into one equation, y equals x beta plus the errors, where that first column of 1s in the design matrix is what carries the intercept. And then a single formula, beta hat equals x transpose x inverse times x transpose y, hands us every single coefficient at once. The reason this is the standard way to write regressions is that the formula doesn't care how many variables or how many observations you have.